Welcome to This Explainer. Today, we're diving into something absolutely fascinating. We are going to decode the literal and visible rulebook of the universe. We're talking about the foundational code of mechanics and Newton's laws that secretly govern, well, literally everything in our everyday physical world. Seriously, take a second and just look around you. What invisible rules are governing every single move you make right this second? Whether you're just sitting there in a chair, holding your phone, or watching a car drive by outside your window, there are these profound, unbreakable physical laws acting upon you and your environment constantly. It's wild to think about. Okay, so let's dive right into this. Here is our roadmap for today. 1. The fundamentals of force. 2. Inertia, or the first law. 3. Momentum and the second law. 4. Impulse and sudden impacts. And finally, 5. Action and reaction, the third law. Section 1. The fundamentals of force, defining movement. All right, before we can understand the laws themselves, we really need to meet the main character here. What exactly is a force? Well, simply put, it's just a push or a pull resulting from an interaction with another object. The crucial thing to remember is that it's always an external agent trying to change a body's state of rest or motion. Force also has a specific direction, which makes it a vector quantity, and we measure the whole shebang in newtons. But what does a force actually do in practical, everyday terms? Well, it produces a bunch of highly visible effects. An applied force can move a completely stationary object, like you pushing a heavy lawnmower to finally get it going. It can stop a moving object. It can change the speed of an object, like a cyclist pedaling way harder to accelerate. It can change the direction of motion, like a football player kicking a ball midair. And, super interestingly, it can even change shape or size. Think of a baker forcefully kneading dough into a pastry. Now, this brings us to a really crucial distinction. Why doesn't a book resting on a table just float away or fall right through to the floor? It's all because of balanced forces. The net force is exactly 0. Gravity is pulling the book down, sure, but the table is exerting an exactly equal upward normal force, so the whole thing just perfectly stays put. On the flip side, unbalanced forces happen when that net force is not 0. Something like a rocket launching into space, or a team actually winning a tug-of-war. Those require unequal, unbalanced forces to cause real acceleration or a sudden change in direction. Section 2. Inertia, first law, resisting change. Enter Sir Isaac Newton and the universe's ultimate rule of stubbornness. The first law of motion states, an object remains at rest or in uniform motion in a straight line unless acted upon by an external, unbalanced force. Basically, if that external unbalanced force is 0, there will be absolutely 0 change in its state of motion or rest. Period. We call this stubbornness inertia, and it actually comes in 3 different flavors: rest, motion, and direction. Have you ever wondered why you practically spill your coffee backward when your bus suddenly lurches forward? That is your body's inertia of rest. Your mass wants to stay exactly where it was. Conversely, if you're cruising along and the bus slams on the brakes, you fly forward, right? That's inertia of motion. Your body just wants to keep traveling at that exact same speed. And if your car takes a super sharp turn, you feel shoved to the outside door because of the inertia of direction. Your body naturally fights any change to its path. Section 3. Momentum and the second law, measuring motion. So how do we actually quantify all this motion? We use momentum, which is just an object's mass multiplied by its velocity. Think about a massive, heavily loaded semi-truck. It has a huge mass effect, meaning it needs a tremendous amount of force to start or stop. But then think about a tiny bullet. It has a massive speed effect. Its incredibly high velocity means it also requires a huge stopping force, despite being so incredibly small. Let's logically connect force right back to momentum. Newton's second law says force is proportional to the rate of change of momentum. Now, if you take the change in momentum and divide it by time, you get that rate. And since a change in velocity over time is just acceleration, we arrive at one of the most famous equations in all of human history. F equals ma, force equals mass times acceleration. Let's connect that math directly back to real life. Why does a cricketer or a baseball player pull their hands back when catching a super fast-moving ball? By pulling back, they're increasing the time over which the ball's momentum changes to 0. A longer time means less acceleration, which vastly reduces the force actually felt on their hands. It is literally F equals ma in action. It's the same reason that the harder you kick a football, the greater the force and the more that ball accelerates. Section 4. Impulse and impacts, sudden bursts of force. Now, in the real world, forces aren't always the smooth, sustained push. Sometimes they are incredibly violent and instantaneous. We call this impulse. It's simply the force multiplied by the tiny time duration it acts upon an object, completely changing its momentum in an absolute flash. Picture a heavy wooden bat cracking against a baseball. Notice the massive spike represented by the curve on this graph. You have this absolutely huge force applied over a microscopic fraction of a second. But even though that time is incredibly short, the sheer magnitude of the force completely reverses the ball's momentum. Section 5. Action and Reaction, Newton's Third Law. And here is the grand finale. Newton's third law of motion states, for every action there's an equal and opposite reaction. Whenever one object exerts a force on a second object, that second object exerts an equal force in the exact opposite direction right back at it. Now, the absolutely crucial point here is that while these forces happen simultaneously, they're acting on completely different objects. Because they act on different objects, say object A and object B, they never ever cancel each other out. To really picture this, imagine you're jumping off a small boat onto a wooden dock. As you jump, your legs push the boat backwards, right? That's your action force. The reaction force is the boat pushing you forward. Or look at the recoil of a fired gun. The explosive action forces the bullet forward out of the barrel, but the exact equal and opposite reaction violently forces that heavy gun backward into the shooter's hand. This constant, endless exchange of forces is entirely ubiquitous. I mean, it's literally how we move. When you swim, you're pushing water backward, and the reaction is the water pushing you forward. When you simply walk across the room, your foot is actively pushing backward on the ground, and the ground pushes your foot forward. Even when a hammer strikes a nail, driving it downward, the nail pushes back on the hammer with an equal force. That's the physical jolt you feel up your arm. It's also exactly why stubbing your bare toe on a heavy coffee table hurts so incredibly much. You hit the table, but the table hits you back with the exact same force. There's just no way around it. It is truly amazing when you step back and realize you're participating in this invisible rulebook every single second of your life. So, I'll leave you with this provocative thought. As you sit here watching this explainer, which of Newton's laws is acting upon you right now? Think about the balanced forces keeping you perfectly in your seat and the inertia keeping you stationary. Pay attention to the physical world around you today. It is endlessly fascinating. Thanks for learning with us.